Determine the intervals of a function that concaves up or down. First of all, what does concavity or concave up or down mean? We're going to talk about that. And what are points of inflection? How do you apply the second derivative test? And we talked about the first. Now, what does the second derivative test tell us? That's what we're going to discuss, okay? Part 1, concavity and points of inflection. Definition of concavity. Let f be differentiable on an open interval I. The graph of f is concave upward, on I if f prime, so the derivative is increasing on the interval, and concaves down if on I, if f prime, or the derivative is decreasing on the interval. So let's look at this, okay? Concave upwards, you can see that it's concaving up and concaving down. That's a general picture. Concave upward, and that means f prime is increasing. You can see this, this is right here is our slope, right? Our derivative. It's increasing here. Now, I want to show you also when it's increasing, you can see that the graph of f lies above its tangent lines. So you see this graph right here? This is graph of the f. This is also the graph of f. And you can see the tangent lines are below. So if the tangent lines are below that line, that means it's concaving up, because that means the slope is increasing. Let's look at concave down. F prime is decreasing, right? You can see that it's decreasing, the slope. And you can see that graph of f lies below the tangent lines. So below the graph of the line, the f, the curve, is below the tangent lines. Okay? And that means the slope is decreasing, therefore it's concave downward. So think about it this way. Tangent line above, that means it's concave down. Tangent line is below, that means it's concaving upward. Okay, you'll get used to it. And always just try to think about the general shape of concaving up or down, okay, when doing these. Not just memorization, okay? So now let's go on with this definition. Test for concavity. The graph of y equals f of x is what? Think about it. When your second derivative, which is y double prime, is greater than 0. So we're going to talk about all this, but just know that it's concaving up, okay? So we say upward, concaving upward. If your y double prime, your second derivative, is greater than 0. We're going to formally discuss the second derivative test later. The graph of y equals f of x is concave down, right? Downward, if y double prime is less than 0. These are definitions in your book too. The point where the concavity changes, we're going to talk about this. This is kind of tricky, okay? The point where concavity changes is called the point of inflection. Remember I told you when I introduced this unit to you, or this section to you, or this whole unit, right? We're going to be able to draw a sketch of a graph knowing all these things. We just talked about increasing and decreasing, right? And the first derivative test. Now what does concavity tell us? What does point of inflection tell us? Using the second derivative test. We're going to discuss all that. You're going to be able to sketch any kind of curve using all this information. Let's go on to here, okay? I need to show you a little bit more. So here's a graph of f of x where 1/3 x cubed minus x. So that's your general curve. It concaves downward, right? Right here, from here to here. And you see this guy m equals 0. That's like our point of inflection because our concavity sort of changes, okay? These are our key points here. Let me rephrase that. These are our critical numbers, and they're critical numbers for a reason, right? This guy is when you're increasing and then decreasing changes. We talked about that using the in our last section. And here something happens here too, okay? I'm going to talk about that later. It's where concavity changes. That's the point of inflection. And as you keep on going down, decreasing, you see how here it increases. This is another critical number for us. Concave downward, concave upward, and you can see here that's our function of the curve of our function here. And this guy is our f prime of this guy, okay, our first derivative. So you can see here, these are our, we talked about this, right? These are our critical numbers. We talked about it here, right? It's where it's increasing and decreasing changes, critical numbers. And you can see something happens here. You see how here its concavity is, it's downward and it's upward here. You can see the concavity of f is related to the slope of the derivatives. We're going to put all that together. Right now, let's just try to understand what's happening, analyze them, stop the video. Before we try this one, let's try this example first, okay? We're going to try example 2 first, okay? Slow down the video and try to digest that and read over your notes as you're working on this. Determine the open intervals on which the graph of this is concave upward or downward, okay? All right, upward or downward. So the first thing we're going to do, you're right, we're going to find the derivative. So why don't you guys find the first derivative right now? Turn off the turn off the screen, okay? I'll do it here too. So you can see that we're going to need the quotient rule. So I've done that here. What I'm not going to show is all the steps and how I got here, okay? So you can see I apply the quotient rule, and here's what I get for my f prime of x. I get, when I simplify everything, I get negative 10x over x squared minus 4 squared. I haven't simplified anything. I'm going to use that later. Here's my second thing. I'm going to do my second derivative, okay? And you can see from here that we're going to have to apply the rule again, right? Using this guy, though. So quotient rule again. So I get negative 10 x squared minus 4, x squared minus 4 squared minus negative 10x, right? Don't forget 2x, and then here, chain rule, right? So 2x squared minus 4. Now stop the video and try to digest what happened here from here to here, okay? Again, chain rules applied and also the quotient rule. Ask each other too. X squared minus 4 squared squared. When I simplify all this, here's what I get. I get 10 3x squared plus 4 all over x squared minus 4 to the cube. Obviously, it got reduced down to a cube. Try to get this, okay, after you simplify. But if you don't get this far and you leave it like this, it could still work. It'll just take you a long time to compute. So here's our f prime, and here's our f double prime, our second derivative, okay? Now, what are we going to do with that, our third step? Are you ready for our third step? We have to find our anywhere that's discontinuous or not continuous or undefined or our critical numbers, okay? Now, I can see from the original that this is not continuous, right? Same step as what we've done before, right? With increasing or decreasing function. It's not continuous at x equals plus or negative 2. You can see that, right? It's undefined at x equals plus or negative 2. Okay? Now, let's find when f prime of x is equal to 0. Okay? Now, we're going to talk about why we're doing this later, okay? When is it 0? So we set this guy equal to 0. This guy right here, we set this equal to 0, and you can see nowhere, okay? None. There are no critical numbers at that point here, okay? So now, let's do our fourth step, okay? Okay, so let's go here like this. Let's actually just do a little sketch, okay? You remember how we do little checks? So let's go like that. Let's make a little number line, and let's do negative 2 and 2, our critical numbers. And let's see what the behavior is, this area here, and this area here. So try a negative 3. So what I've done is I've tried f double prime of f of negative 3. And when I plug that back into this here, I know for sure it's going to be greater than 0. So I know it's positive here. Now I'm going to try somewhere between here. So f double prime of 0. And I got less than 0. I'm going to try some test values here. That's negative. How about 3? And I get greater than 0. That means positive. So you see, I did double primes though, right? So right now we're not discussing increasing or decreasing. We're trying to see if the concavity, right? Where does it concave up? Where does it concave down? Anywhere that's positive here, what do you think that means? It means it's concaving up, right? This means it's concaving down, and this means it's concaving up. So let's conclude, okay? So this comes with our, I guess this is our fourth step, and I would do this as my fifth step, our conclusion, right? Concave up, where? What intervals, right? Concave down, what intervals? So concave up, you got it, negative infinity to negative 2, and 2 to infinity. Okay, this is just checking for concavity and finding our critical numbers using our double prime, okay? Later, we're going to put everything together. Concave down is negative 2 to 2. You can see that here, okay? All right, so I'm going to go back to the former example, example 1, okay? So let's go look at that example again. Now, you try this one. Find the points of inflection, and I'm going to tell you what the points of inflection means right now, actually. Let's discuss this definition that was below here. Theorem 4.8, or points of inflection. If C, f of C, is a point of inflection of the graph of f, then either f double prime of C or second derivative of C equals 0. Look, we have that here, right? oh, that's a special point. That must have been a point of inflection if there were any, but here it didn't have any. Or second derivative does not exist at x equals c. So the point of inflection, two characteristics. F double prime of c at that point is 0, or F prime double prime does not exist at x equals c. Okay, we're going to talk about all these situations here. So here's a graph of f of x at x to the 4th minus 4x cubed. Point of inflection can occur where this equals true and this does not exist. So you can see right here. Look at this. Okay, and look at this. What do you think that means? You're right. F of c is 0 here, isn't it? And notice this is not a continuous function here to here. It's actually just going down. It's decreasing all the way. So this is a point of inflection because your second derivative of f of x, or your second derivative of c is 0. Okay? And here,